Over billions of years, our world has evolved so much that it always keeps us on our toes. Chasing the truth about everything we see and we don't see is a summary of what science has been doing for centuries. And it's not over yet. From the shocking birth of the universe to the emergence of its most mind-boggling phenomenon, black holes. What exactly are they? How are they created? And how their immense gravity forms a cosmic abyss that swallows everything in its way. Stay till the end to find out. Most of us have heard about black holes through documentaries, books, TV shows, or even YouTube videos like this one, and yet a lot of us still struggle to understand them. So what exactly throws off people when it comes to black holes? To answer that question, we must first ask this question. What are black holes in the first place? Before this incredible advancement in technology that allows us to peer into the farthest reaches of the universe, black holes were a mere imagination. First theorized by John Michell in 1783. Though the name black hole was yet to be coined, John Michell argued that there's an escape velocity needed for light to be able to escape the gravitational pull of a star, and this escape velocity may exceed the speed of light for a star that's 500 times the mass of our Sun. Light would then be pulled back into its surface, which will render this celestial object completely unseen to us. Now let's stop here for a moment to explain what is an escape velocity. So let's take Earth as an example. Let's put the International Space Station right there. Now, the International Space Station, or the ISS, orbits the Earth at an altitude of 408 kilometers and at a speed of 7.778 kilometers per second. That is really fast. However, this speed only allows the ISS to orbit the Earth without crashing and without escaping its gravitational pull. Now, if we want the ISS to escape the gravitational pull of the Earth, we would have to increase its speed. So, the escape velocity of planet Earth is 11.2 kilometers per second. So, if the ISS were to escape the gravitational pull of Earth, it would have to reach this speed or more. Now, if the ISS reaches this speed, it would be able to escape the gravitational pull of Earth and venture into interplanetary space. After that, black holes were rediscovered in Einstein's general relativity in 1916, further examined by Carl Schwarzschild when he solved Einstein's equations for warped space around a massive object that is too dense, which inhibits light from escaping, which in turn makes it invisible. In 1968, the term black hole was first coined by John Wheeler. But what exactly are black holes and how do they form? To answer this question, we must first understand that stars are born in the universe and there comes a time when they eventually die, when they inevitably run out of fuel. When that happens, there's a three-case scenario involving the three star masses that we know of. Low-mass stars whose mass equals or is less than half the mass of the Sun, medium-mass stars that reach up to 3 solar masses, and massive stars that are 3 or more solar masses. Low-mass stars turn into a white dwarf by the time of their death. After they enlarge, burning out fuel, the outer layers spread out to form what is known as a planetary nebula, while the core collapses into a white dwarf star. One clear example of this type of low-mass stars is actually our Sun. It's gradually enlarging, reaching a point where it engulfs the inner planets, Mercury and Venus, before it endures what we talked about earlier. Medium-mass stars, however, experience a different scenario. They have a higher core mass, that's 1.3 to 3 solar masses. At the end of their life, these stars experience a supernova, which is a massive explosion. The end result of this explosion is a neutron star, no larger than a city. But these stars have a surface gravity so strong that its escape velocity is about half the speed of light. Now we move on to the most interesting one, massive stars. Here, we're talking about a star that's at least 20 times more massive than the Sun, and whose core mass is over 3 times more massive than the Sun. The sheer size of these stars is almost unimaginable. However, space is abundant in these types of stars. At the end of their life, an event similar to the other types of stars occurs. The star goes into a supernova and its core collapses. But because its core mass is very high, the process of collapsing continues. More and more matter condense into a very small space, as large as New York City. The density of its core increases its mass to range from 3 to 20 solar masses. The mass of this star warps space-time so severely that the escape velocity exceeds the universal speed limit, which is the speed of light. And that is how black holes are born. In other instances, black holes are born out of collapse between massive stars. So now that we know how they are created, let's explore their composition. We can recognize the shape of a black hole from many images online, or from this real image of a black hole taken in 2019. Black holes, however, are often unseen due to light not being able to escape their gravity. But from what we know, this is what black holes are composed of. First of all, we have the event horizon. Now, this is often considered as the surface of a black hole. Though it is theoretical since it doesn't reflect any light, there's little evidence that it's actually a hard surface. This is the region where everything is doomed to fall into the black hole. At this point, there's a concept called time dilation. According to the special theory of relativity, when getting close to the event horizon, time passes significantly slower. And at the event horizon, time goes into a complete stop.
With general relativity, we learn that the gravitational force is best described in terms of warps and curves in space and time. And that's most directly evident at the edge of a black hole where gravity is strong and the warpage of space and time is strong. And the way we see that is, if you were to go to the edge of a black hole, but have, say, strong rocket engines so that you don't fall over the event horizon, so that you can actually, say, stay in orbit around the edge of a black hole, time for you would slow down compared to the rate of passage of time of somebody far away. In fact, if it was a strong enough black hole, a big enough black hole, and if you got close enough to the event horizon, to the edge, be careful, don't fall over, but stay just outside, you might spend a week at that black hole, and you come back to Earth, it might be 1,000,000 years or 1,000,000,000 years have gone by.
Second, there's the accretion disk. These are flat spinning disks of matter, mostly gas, that are pulled by a celestial object's gravity. Black holes' accretion disks are composed of matter near the event horizon that was pulled by the black hole's gravity. This forms a hot and bright, fast-spinning disk around the black hole, which helps identifying them since they neither emit nor reflect light. However, it's important to note that not all black holes have them. Some may have already consumed them. Moreover, as light passes by the black hole, it is redirected through gravitational lensing, a distortion of space-time caused by the black hole's gravity, which causes light to encircle it, similar to a magnifying glass. This light casts a shadow over the event horizon, and this is called the event horizon shadow. It is usually 2 to 3 times larger than the actual event horizon. Moving on, looking at the black hole, we can actually see light orbiting the black hole. When reaching the event horizon, this light forms a thin circle before escaping, allowing us to see it. This light may have orbited the black hole 2 to 3 times. After matter is forced to orbit the black hole, forming the accretion disk, at the center of this disk, electrons get heated into millions of degrees, which forces the emission of extremely hot X-rays into the opposite directions of the accretion disk. These emissions create clouds 1 billion degrees hot, and this is what is known as the corona. This is especially mentioned by Stephen Hawking, when he argued that black holes could have entropy and could emit radiation. Hawking also stated that black holes or their event horizons should never shrink. This theory has been observationally proven by scientists from MIT. Now, for the most controversial part, the mind-boggling concept of the singularity. A singularity is a point that is infinitely dense and infinitely small. In mathematical terms, a singularity is a concept where an equation gives infinite results. General relativity's equations used to model black holes or their center resulted in infinity or singularity. It is the point where general relativity catastrophically fails. A singularity is theorized to be a point which is no longer a part of space-time, therefore, the questions where and when no longer apply. And this singularity is said to exist at the very center of black holes. Recently, a crossover between general relativity and quantum mechanics is being pursued to produce the theory of quantum gravity, which, under the perfect conditions, might explain what is happening at the center of black holes. However, black holes can cause a lot of misconception for people. Many legends and myths have been created saying that if someone gets into a black hole singularity, they may get out in another time dimension. The fact is that we don't know what's happening inside a black hole singularity, and since general relativity failed to explain it, there's a shift towards quantum mechanics to maybe find an explanation for it. Now let's explore the types of black holes, starting with the smallest, stellar mass black holes. These black holes result when a star that's over 20 times more massive than the Sun explodes at its dying stage. These black holes are from 5 to 100 times more massive than our Sun. One example of this type of black holes is Cygnus X1, located in the constellation Cygnus, and it's about 7,000 light-years away from Earth. This particular black hole packs a mass of 21 solar masses. The second type of black holes is supermassive black holes. These monstrous beings are one of the most intriguing objects in the universe. These black holes are mostly found at the center of every galaxy. There's scarce evidence of how they formed, however, scientists argue that they may have formed from collisions between massive stars, or they may have consumed nearby objects like stellar mass black holes or neutron stars, which made them grow into this supermassive state. The most massive one, however, is TON 618. It is a quasar that contains the most massive known black hole of 61 billion solar masses. And quasars are an extremely active and luminous type of active galactic nucleus. These form from so much gas and dust falling into a supermassive black hole, which causes it to emit electromagnetic radiation across the whole electromagnetic spectrum. Now we move on to the most controversial ones, intermediate mass black holes. These are the missing link when it comes to black holes. Scientists argue that there's a huge mass gap between stellar mass black holes and supermassive black holes, and this gap should contain black holes that are hundreds to hundreds of thousands the mass of our Sun. Efforts are still being made to discover one of these black holes, and maybe we can lay our eyes on one of them in the future, especially with advancement of technology and telescopes. In light of what we have seen, the universe continues to provide us with the most shocking findings that the human mind can comprehend, from supernovae to the formation of arguably the universe's most mysterious objects, black holes. As time goes on, we're discovering more and more of our world in this century than we did over the past centuries combined. The older generations of scientists have provided us with the blueprints, and now it's our turn, with the ever-ending and incredible advancement in technology, to continue their work and explore what may have only been described as theories and hypotheses, to turn them into modern types of blueprints that may help us even discover new worlds. Don't forget to support us by subscribing to the channel and liking this video. We appreciate everyone stopping by to watch our videos. We hope we have provided you with helpful knowledge. Remember to hit the notification bell to stay tuned for more captivating explorations of the cosmos. This was Sounds of Heaven. See you in the next episode.